laureates in physics this year is Pierre Agostini, Ferenc Krausz, and Anne Lollier. And it is my pleasure now to introduce our first speaker, and this is Anne Lollier. So please join me in welcoming Anne.
So good morning. It's a pleasure to be here, and let me start by thanking the Royal Swedish Academy of Sciences and the Nobel Foundation for this prize and for the pleasure, the privilege to give this Nobel lecture. So I will tell you about how we arrived to these attosecond pulses. This is a history of attosecond science with the first years, progress in technology and in understanding, measurement of attosecond pulses, and then opening to research fields and applications. And I will go through the first two parts and leave part 3 to my co-laureates, measurement of attosecond pulses. I will, in the end, just say a few words about some applications. Nothing would have happened without the invention of the laser in 1960 by Theodor Meinmann. And the Nobel Prize in Physics was given to the background for laser in 1964 to Townes, Bazoff, and Prokhorov. And you have here a picture of one of the first lasers, a ruby laser. Now, what we are going to use in our research, the properties of the laser, are first the possibility to generate short laser pulses, and especially the possibility to, by focusing these pulses, to achieve a very high intensity. Now, if we plot the intensity distribution of these high harmonics, we get a typical behavior with the decrease, a plateau behavior where all the harmonics have the same intensity, and this is ending with a cutoff. And this was very unexpected. First, it was not expected to see so many high-order harmonics. Then, it was not expected to have this plateau behavior. One thought that it would be more and more difficult to generate high-order harmonics. This was based on some kind of perturbation theory thinking at the time, that based on an expansion of the polarization induced in the medium in powers of the electric field, for this expansion to be valid, one has to assume that the first order is much larger than the third and much larger than the fifth. And this was not the case. You can notice that I'm only talking about odd orders of the laser, and this is due to a symmetry property of the medium. It has the inversion symmetry, so the even order harmonics are actually killed. Now, if you go from a frequency of the laser light, which is in the infrared region, and you multiply this frequency by, let's say, 33, you end up in the extreme ultraviolet region of the spectrum. So it's below X-rays, but above ultraviolet light. So this light is invisible, and it does not propagate in air. So we have to mention is really going into a completely different direction now, very applied, and this is now belonging not to the research laboratories anymore, but to industry. And this is an application not so much about the temporal structure of these high-order harmonics, not so much about attosecond pulse, but about simply an application of this radiation, which is in the extreme ultraviolet range, and which is very broad in frequency. So now harmonic generation are being used to control wafers, silicon wafers, which contain integrated circuits, and this technique is used for the next generation instruments that will control this integrated circuit with very, very small dimensions of the order of 10 nanometer or below. And this control is made not only in 2D, but in 3D. And what is really used here is the fact that we have so many frequencies. And this is developed by an industry, ASML in Holland. Now, to conclude, I would like to thank many people, all of my colleagues during all of these years. And I'm showing here some group pictures, not since 1987, just the last 15 years or so.